Maybe I take first a little bit of water. So thank you very much for the invitation. This gives me the opportunity again to visit one of my favorite places, cities of the world, Vienna. So I have to also to apologize a little bit because my topic is not higher structures. So you will see, but indeed it is related to field theory. Even if I do not talk about field theory, but I guess you might. Those who work in field theory, you might see where there's the connection to field theory. So, good. So, just to give you some general points and so on. So, of course, everybody in the audience, maybe I should first say, please stop me if I'm too fast. Of course, I hesitate a little bit just to go into it too slowly and so on, but nevertheless, in the computer presentation, one tends always to be a little bit too fast. I like to be interrupted. So people who already heard me, they know that I like to be interrupted. So so the classical genus zero algebra. This is in this context the two-point algebra. This is Witt algebra, Virasoro algebra. And also affine Kac-Moody algebra, and so are well established. Of course, everybody in the audience knows about them, and of its relevance, e.g., in conformal field theory, or more general, even there. And from the application, now let me see whether this also works. Yeah, okay. From the application, there is a need for a multipoint algebra in every genus. Of course, also including the genus zero, the multipoint situation. So in genus zero, you will see in few slides, you will see what this exactly means. And now the higher genus and still 2 points. This was done by Krichever and Novikov a long time ago. And the multipoint theory was done to a large extent by the speaker, by myself. So it's this is one of my research topics. And this was 87, 86. And I started this business also a long time ago. There was in the starting in the 90s with my PhD, but then maybe a couple of years ago, I wrote a monograph about this Krichever Novikov type algebra. So I developed it further, and and this algebras there are also nicht some logical equations for genus zero. Sorry, this is nowadays classical, but then this can also be done in higher genus in the context of the moduli space of genus G curves with n marked points, and there one can use this Krichever Novikov multipoint algebras. And this was done, I did together with Oleg Scheinman from Moscow. I don't know exactly what I don't know what he was doing. Okay, but I will check. I will check. Yeah, but there was recently there was now again revived interest in genus zero multipoint situation here. If we were of course heading towards the general thing, and there was a genus zero multipoint situation, and in this context they used the name endpoint Virasoro algebra. And this was now in some sense my starting point. And now the goal of this presentation here, the recently discussed endpoint Virasoro algebras, which are some names, Cox, Durisic, Martins, and others, are special examples of the multipoint Krichever Novikov type algebra. Of course, you might ask, and this would be completely right, what do I gain if I see that this kind of algebras are special cases of another more complicated type of algebra? But the point is that by this process, one gets structural insights and an easier approach to calculations. If you check these original papers there, you They are calculations which are horrible in some sense, and they are done without any, I shouldn't say without any insight, but with not so much insight and so on. And in some sense, this is the lesson to be learned again in mathematics, generalize the situation and understand the structure better. This is a very typical example because by generalizing the situation, you get what is really behind it and so on. You will see it, what's going on. And the side effect, but this maybe is not so much of importance for you, I could remove some misconception about certain observed phenomena. So there were some claims which were, from my point of view, absolutely clear that they cannot be true. But in their approach, it could not be shown. Okay, good. I guess this is, okay, I should also say what I will do now here. I will recall the geometric setup for Krichever Novikov type algebra. I try to be rather short and maybe concentrate on what I really needed in this context for this talk. But extremely important, of course, I introduced the algebras, not only this Virasoro type, but also the whole family there. There is an almost grading, including triangle decomposition. This is an important point. This classical Virasoro algebra, classical Virasoro, Witt and so on, and affine algebra, these are graded algebras. So in general, this higher or even multi-point genus 0 and higher genus are not graded anymore. So, but the point is, why do we need a grading? We need a grading in a certain sense for representation theory. So if you cannot talk about Werner modules if you do not have, or maybe let me change it a little bit, you cannot talk about Werner module, you cannot talk about annihilation, creation operators without having some kind of a grading, or maybe maybe if the grading is not there, to have at least a weaker concept. And this weaker concept will still do the X to this situation is this almost grading. And this is what allows you to construct such kind of representation. And then determine all central extensions. Why do we need central extension? Of course, maybe there's no need for you that I tell why. So central extension are in the process of quantization. We are forced to pass from the algebras, from our classical, I should be careful because now I don't talk about the classical, I talk about the Witt algebra, let's say. Then just to construct representations which show up by quantization procedure, we have to pass from the Witt algebra to the Virasoro algebra. And this is exactly here also in this general context, of course, necessary. So but regularization, subtraction of infinity is in some sense everything the same. So for this, we will need it. Okay, good. This is in some sense the program. And now I will start the program. Then I will start the program, but I tell you first what will be the outcome. Okay, good. For Krichever Novikov type algebra of genus 0, I will explain immediately in more detail what they are. I will give all co-cycle classes for the vector field algebra, the differential operator algebras, and I will show that they are geometric. And I give the, Yes, what we will have, this will show up. So I will talk a huge mother algebra in some sense. And this mother algebra contains all these algebras which we need. These are the function algebras. These are the vector field algebra. These are the differential operator algebras. These are the superalgebras. They are all contained in this mother algebra. I will introduce this mother algebra. And of course, then the derived stuff like affine algebras, affine type algebra, I should say, and so on. These are these algebras. So this is here, you see. This is this current algebra, which is down here. And the Heisenberg algebra, this is the central extension of the function algebra down here. Okay, and as an illustration, I will close the talk with a 3-point genus zero situation, just to give us some kind of feeling there. Okay. But now I start really with it. So, very good. Thomas already interrupted me several times, but let's take this as some encouragement also to interrupt me. So, of course, I know, I'm pretty sure everybody knows this here, so maybe I go too fast through this here. So we have in purely algebraic terms, the Virasoro algebra, this generated by En, by this generators En running to the integers, and a central element T, and we have this well-known relations there. This is the Virasoro cocycle there. If the cocycle is not there, so this T is a central term, I should have also written it, TT is 0. I forgot to do it. Without central term, this is what I call the Witt algebra. Of course, there is discussion whether one are really able to call it Witt algebra, but I don't care for the moment. I call it Witt algebra, okay? Yeah? Okay, good. Good. This is a Lie algebra 2 cocycle, okay? And of course, we can make a cohomological change. So this is this N, for example, this is only a certain kind of normalization of this co-boundary, okay? We can add other co-boundaries. We get the same isoclass of the central extension. Let's say we get the same central extension up to equivalence, okay? But it's only one-dimensional. This is the cohomology of the Witt algebra. H2 Witt algebra with values in a trivial module C is one-dimensional. So there is only up to equivalence and rescaling only one central extension. So this is a certain scaling chosen, and this one comes from choosing a certain co-boundary. Essentially is that here we have a cubic term. We can also write the stuff as n times n plus 1 times n minus 1, and then we still get this. But we can even get rid totally of this n. But it's just a co-boundary, okay? Good. Okay, good. Now, from this, starting from the Witt algebra, we can now also consider this affine Lie algebras. We have this finite dimensional simple Lie algebra with a certain cut-and killing form, and we introduce this algebraic relation. So this would be just, without a central term, would just be the current algebra. And here we have this additional central term there. Okay, good. Just to remind you about the classical algebra, they will show up now for the higher genus here. And this is now the geometric setup. This is now the geometric setup. So for the Krichever Novikov type algebras, you see, it's not necessary that genus is different from 0. Even you see, we start with a compact Riemann surface. Here, a compact Riemann surface could be genus 0. Okay, good. And but the G should be the genus, and we have a finite subset of this Riemann surface. So it's just finitely many points. This I denote by A here, but this set of points A is split into 2 non-empty subsets, which are disjoint. I call them I and O for in points and out points. This is the idea when I did this, the context of string theory. So this one is the worldsheet of the string, and we have incoming points and outgoing points. So from this interpretation, one has a natural separation of this set of points from incoming to the outcoming. And if you have incoming, you need also some outcoming. So by conservation laws and so on. So good. No, this was the wrong pointer here. So in genus 0, genus 0, we can say, okay, this is now a Riemann sphere, okay, a genus 0. We have n points, P1 up to Pn. And let me already just give you this kind of normalization there. So one point, let's call it the last point, it could be brought to infinity by fractional linear transformation. We talk about the Riemann sphere. So there is the point at infinity. And so this set A does not consist necessarily where the point has the point at infinity, but we can, by fractional linear transformation, this is just a conformal transformation of the soil situation, we can bring one point to infinity. This is not, yeah, okay, okay, no, why? No, yeah, okay, you're right. Here I have P1 up to Pk. Here I have P1 up to Pn. And K will be, so now, no, sorry, I should not say it like this, because what is in and out is a choice, and the theory will depend on this, okay, good. So here we have K plus M is equal to N. K plus M, this way I should say it. K plus M is equal to N. Okay, good. And now, I can bring in this, I can bring the last one point here, I can bring it to infinity by fractional linear transformation. And what I gain by this, I can identify the points Pi by this complex coordinates there, by complex numbers. The points, these are now at the finite part. Yeah, yes, good. So I have here this, and the coordinate would be, local coordinate would be z minus AI, for example, but the points correspond to AI. And the last one corresponds to infinity, okay? And in this case, I have local coordinates. I already said it here, this one. And here I have to take as local coordinate 1 over z to get this local coordinate at infinity. Yeah, the situation is that maybe it looks a little bit like that this is already a splitting, but we won't. It is important not to mix these two concepts there. Here it's only that there some kind of a description of the points on the sphere. The classical situation would be S2, so this Riemann sphere, and now I have the point 0 and infinity. And now, of course, there is only one possibility of splitting. We have the one point is in point, the other is the out point, okay? And so conventionally, the in point I put to 0 and the out point to infinity. But there is no natural splitting if you have more than 2 points, okay? There is no natural splitting. Good. Okay, but I will return to this in the examples where we have 3 points. So we will see clearly what happens there. But now first I have to explain a little bit so how these algebras are constructed here. The starting point is we start with a canonical bundle on the Riemann surface. I talk about the general situation. The canonical bundle, these are the bundle which local sections are the holomorphic differentials. Yeah, exactly. So these are those with Fz, Dz, okay? Where F is now Fz, Dz. This is the local description of this here. Yeah, so Dz is a one, but of course, locally, the differential looks like Fz, Dz. Yeah, Fz, sorry, Fz, Dz. And now, but I also consider k power lambda, lambda the tensor power of this canonical bundle. Here in this talk, I concentrate on lambda, an integer. But lambda can also be a half integer. But then I have to choose a square root of the canonical bundle, meaning which is a spin structure, let's say, square root of a canonical bundle. So we have 2 to the power 2g of them. So for g equals 0, we have only 1. For g equals 1, we have already 4 of them, 4 spin structures. This is an additional choice now which we could do. But I will skip this because we are in G equals 0 interested, and there is no special choice here. But if we want to talk about now in the following about superalgebras, of course we would have to do it, but I will not do it in this talk here. Good. So we ignore the half forms here. This would be the C super case. But if you want to know more, I will give at the very end the reference of the original article, and you can check it in the original article. So now we have the bundle. Now we consider F lambda. So I put here A because we say it depends on the A. These are global meromorphic sections of K lambda. Meromorphic means such that, let me finish the sentence, such that F is holomorphic over the complement of A. So they are meromorphic sections which have only poles, possibly poles at the points in A. Okay, good. It should be an algebraic pole. This is the definition of meromorphic, okay? This is in the definition of meromorphic. This means, I said, we can write them locally as Fz. Z is the variable, dz, okay? So meromorphic forms means the Fz could be a meromorphic function, could have poles, okay? Algebraic poles, okay? No, this is not fixed. Could be arbitrary, okay? It could be arbitrary. Could be arbitrary. So these are, you see, infinite dimensional vector spaces. If you fix them, it would be finite dimensional, but then we would not have the algebraic structure which we are heading for. This we call sorry, meromorphic forms of weight lambda. Good. Now, this mother algebra, so this up to now is only a mother vector space, okay? This is now F, the direct sum of all these F lambdas. Here I already even wrote down half Z, but this means, of course, if we take half Z, we have to fix a theta characteristic or spin structure, or square root of the canonical bundle. Okay? Good. Now this mother algebra said already algebras are the algebraic structures there. Okay, I don't want to go too much into the details, not because I need to go to this what I really want, this genus 0 situation. So, but please tell me stop, and I will explain in more details here. We have this associative product structure. If we have a form of weight lambda here, a form of weight nu here, we just multiply these two forms. So this means that we have the functions dz nu times function dz or lambda dz nu, multiply them just by locally multiply them, and then we get now a form of lambda of weight lambda plus nu, and it's just this one here, locally description. And now you check easily, this is more or less trivial, that this F is the big F, all lambdas contained, all lambdas, is an associative and commutative graded algebra, where the grading comes from the lambda. Sorry? Yeah. Lambda is in my presentation here a C value, but lambda is indeed possible to be half integer value. So if you want to talk about the superspace, we have to also allow lambda half value. Interesting point. So of course we could construct some kind of maps there, where then the lambda is a certain, maybe some kind of a kernel or what. This might be possible. I did not think about it. It's a direct. Yeah, okay. This is something I would. Yes, we will have to see that the whole thing, that a whole lot of stuff depends on that the splitting is respected by this process. We will see it maybe on one of the next slides here. Okay, the point is this: if F0, so this means if you only consider F0, then this is a subalgebra, because 0, 0 gives 0, okay, we stay inside. And all these f lambdas here are modules over this A. F0 is just functions, and all forms of weight lambda are modules over the function. This is, of course, something rather trivial. I said this is rather trivial, but nevertheless, it is good to have a general look on this here. This is really commutative, okay? There will be no braiding show up here. The next structure is a bit more interesting. So this is the Lie algebra structure. So here we have lambda weight, nu lambda, and then it goes to lambda plus nu plus 1 weight, okay? And this is, the point is, in local representing functions of weights, it can be expressed like this. So if lambda and nu is -1, it will end up in -1 again. Okay, good. So f -1 will be a substructure here, but this is quite very general here. This is true for everything, and now one shows that this is a Lie algebra. So we have f is also a Lie algebra. And of course, the F is an associative algebra and a Lie algebra. And of course, the next question, is it a Poisson algebra? Yes, it's a Poisson algebra. So this big F, this is what I call the mother algebra. The mother algebra is a Poisson algebra. But it's really infinite dimensional. And it has a certain grading coming from the lambda. So as I said already, F -1 is the Lie algebra, is a Lie subalgebra, and it's the algebra of vector fields. Because weight -1 means vector fields. This is d over dz, okay? Just this is the vector fields here. And in addition, the f lambdas are Lie modules over L. Okay? Because you say they come from the big Lie algebra. Hence, so this is there. It's a Lie derivative. It's the Lie derivative. Yeah, maybe I should have said this. It's the Lie derivative. Yeah, so then it's a Lie derivative. There, but then it's also possible. You see, this mother algebra contains also other subalgebras. For example, F0 and F -1 functions and vector fields. This is the Lie algebra of differential operators of degree less or equal to 1. You can easily check that this closes under this, and you get it. And again, these f lambdas are modules over these differential operator algebras. And now you can even go further. You can even consider, but this I said I will not say, but nevertheless, let me say it. So if we take now 0, and if we take f, but now this is only for half integers, okay? If we take again, sorry, f0, and now f -1/2, okay? We get superalgebra. We get the Neuve-Schwarz superalgebra in this context here. But again, I have to refer to this, or we can discuss it in private then here. Okay, good. That is now the algebra. That's the algebra. Good. But now I have to talk a little bit about the almost graded structure. The classical algebras are graded. So as I said, this grading in the introduction is important for defining representations of relevance in the application, like semi-infinite forms, which are necessary for second quantization and such kind of things and so on. Or maybe for the mathematician, they are necessary because they're interested for representations by its own. So, but in field theory, you are interested in this representation from this point of view. In general, the Krichever Novikov type algebra will not have a non-trivial grading. Of course, they have always a trivial grading, but this is not of any help in this context. But there is a replacement which still allows to construct these representations. And this is the almost grading. Don't go too much in this formality here. You see, we have the algebra L, a Lie algebra or other algebra, doesn't matter. We split it into subsets. Into subspaces. It's a vector space. Vector space direct sum into subspaces, indexed by n or by half integer, okay, good. And we call it almost graded if the dimension, individual dimensions is bounded, is finite, sorry, I should say is finite. And you see, if I would be a honest grading, I would have Lm is Ln plus m, okay? Almost grading, there are constant, independent of n and m, there are universal constants. And this means a Lie algebra bracket or associative bracket, because I say an algebra, then it's the algebra dot, but it could also be just also the Lie algebra. So I talk about both. So this is just an algebra operation, which we can rewrite as a point, and typically of associative case, or as a bracket, and then it's a Lie bracket here. But the important point is that we are just in between. So the n plus m would be the ideal stuff, but we go a little bit down, maybe a little bit down, and maybe a little bit up. So good. So there is something which is in this application even always the case. This dimension is even bounded independent of n in this situation which we consider, but it's not really necessary for the definition. Okay, good. This is the almost graded structure here. To keep in mind it is just nearly graded. This is the reason that I call it almost graded, nearly graded, but it just deviates a little bit below and maybe below, maybe above. Okay, good. So now we want to introduce a grading, an almost grading for the f lambdas here. And this is done by exhibiting certain basis elements of this f lambda here. The point is, you see, this one, don't spend too much attention to this. This looks rather horrible. So we have f and p. So this is the lambda weight. N is the degree, okay, is the degree. And p, this just indicates the points, 1 up to k. But of course, maybe I should have written also down what is k. K was the number of incoming points. So they are numbered by the incoming points, not by the number of all points. Only the incoming points will appear there in this labeling. Exactly. By a fixed lambda, it is k. Did I write it down? No, okay, but it's a basis. I said it's a case. Yeah, it's k. K is the number of incoming points. In our situation, it's really always k. I said it is always bounded, but you can do it in a more general situation, okay? You will see why I defined it like this. So now this is what I maybe should ignore in some sense. And these elements are fixed by prescribing the order at the incoming points, okay? By this value here to make it, and then at the point pi, and then the prescription of points in O is made such that it's essentially unique. Without telling you really what I mean by essentially, in general means up to scalar, okay? Scalar, multiplication with a scalar. But there are certain special cases where one needs some additional prescription, okay? Good. But this is the important point. The basis elements depends on the splitting of A into I and O. It's not something which is intrinsic in the situation. So situation, of course, F lambda depends on big A, okay? But this alone does not give you the almost grading. We have to start with the splitting, and then we can fix the almost grading. Starting with the splitting, okay. Okay, but you have a question in mind, Thomas? You're looking like. Yeah. Very good question. So the point is, you see, the algebra is always the same. The algebra is always, at this big F is always the same. But the grading will be different by a different splitting, by an essentially different splitting. Essentially different splitting means it's not just a switch of a role of I and A. Yeah, exactly. No, sorry. Then I answered you incorrect, because I had in my mind that you say, okay, the dimension of the f lambda n. You see, where is it? Here, you see. Right. Here talk about f lambda n. Right. This dimension is k, okay? But the big f lambda is the direct sum of this f lambda n, where I sum over n. There, if I take now an essential difference splitting, which is not just switching the role of I and O, then I get have the same algebra, but it will have a different decomposition. Okay, good. It's yeah, and I would not say it's shift operator because yeah, but it's more difficult. No, it's not even a shuffle, you see, because these spaces do not have any relation. The subspace do not have any relations in between, also between each other. So it's really something completely different. So okay, maybe the example you will see that it will. You see that the point, if you have 2 points and 1 point, this is where you can see something. Then whether you put the second point to the outcoming or the incoming makes a huge difference. They are not really related. You cannot say, okay, this you can just. Of course, you have each element can be written down as a sum because it's a basis, still a basis, but there is no relation. A useful relation, let's say, between these two different. There is not. The total algebra is always the same. It's not even isomorphism. It is fixed. The total algebra does not change. The decomposition changes in an essential manner. So if you talk about, let's say, about gradings, so gradings introduced. Filtration introduced by these gradings, you will see that I will not bring it here, but you can check it. The book, for example, you will see that the gradings the introduced filtrations are not equivalent. So there is no relation between these different decompositions. Okay, but there's interesting questions here. So now we come to genus zero. Genus zero, and there is a certain which I will call standard splitting, but this is not the only splitting. This is where we should keep in mind. But I want to talk about a special splitting where I have now the incoming points consist of this P1 up to Pn-1. This is now our K. And this outgoing point is just 1 point, this one which we brought already to infinity. Good. And in this case, it is it's just enough to construct a basis of the A's of the functions. As then we have Fn lambda is now, you see, now we can decompose the A as direct sum of ANs. And now the Fn lambda is just the AN minus lambda. There's this useful shift by the weight, dz lambda. And these are the elements there. This is if you work in conformal field or work in conformal field, this is well known to you that you have the shifts there. So we'll take the weight of the form into account to get the degree. And this is here, the case here also. There's a normalization factor. It is useful to normalize them that at the incoming points here, it starts with 1 if you take this expansion here, or this Laurent expansion, I have to say. And but don't pay attention to this. The order at infinity is always, in this case, fixed, because we know how it is the order of these forms and functions at the finite part, and then it's already, of course, fixed at the infinity here. This would be now the vector fields. So E and P would be AN plus 1. So this means we have a shift of the degree. P the same P, D dz. Okay, this would be there. Okay, good. But in the general situation, so these above algebras are all almost graded algebras. But again, the almost grade depends on the splitting of the set A, okay? And we have this f lambda is f, in some sense I already said it before, this is now f m lambda, m runs over the integers or over the half integers, including the half integers, let's say, if we want to consider spin structures. Dimension is, as you recognized, is already k of this fm lambda. Here you see the k, this is incoming number of incoming points, or it is in this standard thing, it is now this n minus 1 for genus 0 standard. But important, yes, this is something which has to be calculated and so on. So we have this kind of, indeed, we have such kind of bounds here. R1 and R2 are independent of n and m, and we get here, we start the ideal value, and then we go up a certain number. Here, the same ideal, go up a certain number. Okay, good. So this R1 and R2 depends on the genus and on the number of incoming, number of outgoing points, meaning on the splitting, okay? Sorry, let me repeat again. The A was this algebra of functions. A was F0, okay? A was F0. Yeah. So you see, we have the point, here we have the F lambda. If I put F upper 0, I get A, okay? Yeah, it comes from the basis, so it comes from these prescriptions. How I fix these elements here, and I say, okay, those elements were generated by this. With a fixed n, they give me the basis elements here. Okay, good. Just to give you some idea, though this is not so important for the following here, in the genus 0 and the standard splitting, you see, as I said, depends on genus and the splitting, okay? Genus 0 and standard splitting, we get these values here. 0 and 1. 0, 1, and 2. So for the functions, we have only one step higher as the ideal one. For these least structures there, we have a 1 and 2 step higher. For example, these are for the vector fields, yeah. But the point is, okay, that's true, I did not mention it here. This is also, you see, we have also graded modules. This is also true for the modules, okay? But let me say, let's stick with the Lie algebra, okay? Good, with the vector field. Now, this allows us to have a diagonal decomposition of our algebras. We have the positive here. We have the negative one, but the negative one which are below the certain constant minus Ri. So, and they close for algebras because by the almost grading, these are sub-algebras. These are sub-algebra of U. U is any of this algebra which we discussed above. U bracket minus is also sub-algebra of this U because of the almost grading. We start from minus R1, then plus minus R1, and we get minus R1 plus minus R1, and then we have number plus R1, and still we are below minus R1. So we stick in it, okay, good. But and then we have this in-between part, which is only a vector space in general. We call it the critical script, but it's just a name. This is only there. In the genus 0 classical situation, 2 points, indeed, this one is just one-dimensional, okay? This consists just, let's say for the vector field, just from E0, okay? These are the En positive, these are the En and negative, and then this is the E0. This is exactly this. These are annihilation and creation operators exactly. But in the classical 0, okay. But here in this case it's more difficult, not difficult. Yeah, it's more complex, I have to say. The creation operators consist on this here. If you take this one together, you have also to take into account that you create states by these elements there. In some sense, the geometry is completely encoded inside of this. the moduli of, let's say, if the Riemann surface, there you have 3g minus 3 parameters. There you find here elements here, vector fields there, the vector field situation. You find elements there which represents this deformation direction on the moduli space. And this is in some sense the starting point of the Krichever-Novikov or Virasoro Witt theory of higher genus, which I did together with Oleg Scheinman. But this is not for today. Okay, now before I come to central extension, and that's why it's of course important here, I have to talk a little bit, I have really to talk a bit more about the geometry here. So we consider positive oriented deformed circles around the points Pi. These are deformed circles in general here. Sorry, this is too fast. Again, also positive oriented circles around the point in O. And now a cycle on the Riemann surface is called a separating cycle if it is smooth, positively oriented of multiplicity 1, and it separates the in points from the out points. Sorry? A cycle is a cycle is, you see, you have this, this is a curve, you see, which ends again, a starting point is the end point, okay? Is it really a, it can have more components. No, it could have more components. Maybe it had this. This was this O or Q, and this was P1 and P2. A separating cycle would, for example, be this one, okay? It would also be this one. Because, you see, this has two components. It's not just a S1, so it could be many S1s and so on. It could be also this one, also S1. So this would be a separating cycle. Okay, good. But now we integrate meromorphic differentials on this Riemann surface without poles in the complement of A, okay? Over closed curve. This is a closed curve here. Hence, C and C prime are equivalent if C is equal to C prime in this homology group of this Riemann surface where we remove the A. So only if this one is only responsible for the outcome. This homology class of the cycle is responsible for the outcome by the integration. Maybe if you see now how we use it, it might be clearer. Separating cocycle is always equivalent. I say equal, but I mean equivalent. It's equal in the equal in this homology group, okay, or space. If it can be written as the sum over the circles around the incoming point, or minus the sum of the circles around the outgoing points. But it can be different. You see, this one represents the CS, this one represents the CS, and the collection of this one represents also the CS. Because by like Stokes theorem is it called? By Stokes theorem, the integration value will be the same. And indeed, you can give a homology operation between them here. And this allows us, if we have a separating cycle, we can now define a map from F1 to C by integrating a differential form, also element of F1, over this cycle CS here. Indeed, this integration corresponds to calculating residues, okay? Good. And the Krichever Novikov duality, which plays an important role, but I don't think that I will have time for on the to command this anymore. So this gives now a duality between f lambda and f1 minus lambda. By just taking this product, gives now one form and integrated over CS, where the integration over CS can be done by calculating residues. So, okay, now central extensions, but you already said second Lie algebra homology. So of this algebra, you should any of these algebras. U is any of these algebras. I mean, you mean A functions, L vector fields, D differential operators, or these current algebras, any of these algebras. I denoted by U. I denoted it when I talked about the triangular decomposition. Okay, good. U, any of these algebras. The point is, I want to now classify central extension of an algebra U. Okay. Sorry? It could be in principle be all of F. Yeah, this is true. Individual F lambda is not necessarily an algebra, but F0 is an algebra, F minus 1, and so on and so on. So, good. Now, the point is, the perfect Lie algebras admit universal central extensions. This is some mathematical statement. So, you see, how's the relation? I think everybody knows. Maybe perfect, what a perfect Lie algebra is, maybe not to everybody known. Who does not know it, what the perfect Lie algebra is? Sorry? Yeah, who doesn't? So, a perfect Lie algebra is this one. The commutator of U with itself is U. Okay, good, that's simple. And for example, simple Lie algebras are perfect. Semi-simple are also perfect, but there are also others which are perfect, which are neither semi-simple nor simple, okay? So, sorry? Yeah. So exactly. So it's so the mathematical statement is that perfect Lie algebras admit universal central extension. What? So that all central extensions are surjective images of the universal central extension. Maybe you will understand it a bit better. But okay. So all central extensions come from the universal central extension. The universal, you see, the point is the universal central extension is not just one-dimensional in general. It is, let's say, t-dimensional, let's say. But now, if you have a one-dimensional central extension, you know this is a surjective image from the universal central extension here. This means always universal. And in universal, everything is contained. Okay. It is. Exactly. Yeah, perfect. I think it's not necessary that I explain the context of this. What this has to do with the central extension, but okay, if you want, please tell me. If not, I will not do it. So, that now I talk about geometrical cycles. Geometrical cycles, they are given by co-cycle from U cross U to C, okay? And I could construct such co-cycle by taking some gamma hat, which is now a map from U cross U to F1, defined in a universal geometric way, which I will not describe in more detail what it really means. And then integrated over a curve C. Now, you see, if a gamma hat is fixed, given the gamma hat, only the class of C in this one plays a role. Only the class in this one. The point is, you see, this H2, U, C, we cannot easily grab on. We cannot find it directly, but this will give us a way to do it. So here we have now this H1. This is some geometric stuff. This is well known here. It depends on the genus, number of points, and so on. This is this formula there. Okay, good. And now genus 0 and n bigger than 1. From non-homotopic, this depends. Now this you can this you cannot. This depends on this gamma hat. If they are really different, so okay. So if the gamma hat would be holomorphic differential, you get always 0. Okay, good. The point is that it as holomorphic everywhere, I should say. So you would have to have poles somewhere. But indeed, you can find them correspondence, but this is some work to do. Okay, good. This is some work to do. So the dimension of H0 AC, this is n minus 1. That's clear. It comes from the formula there. You have these circles and so on. And a basis now of this is given by circles around the pi, where we leave out of one of them. Pi goes up to p to infinity. But for example, so this would now be a basis of this homology, okay. But a better choice for the standard splitting, take Cs to be minus C infinity. And Ci up to 1 n minus 2. You will see, hopefully, you will see why it is a better choice. Good. Now I have to be very fast in this context, but nevertheless it's important here. You see, so we want to extend our representations, let's say, from the, if you do this regularization procedure, from our classical non-extended algebras, we will or the representation of this, we go over to this kind of semi-infinite wedge forms, let's say. Then we have our algebra does not act anymore. We have to go to the central extension, but we want to construct the central extension by in the independent way to classify them. And now the point is that we want to extend the grading, this almost grading, to the central extension. We want to extend this to the central extension. And now, if we have only take some co-cycles, this will not work. We have to consider, for the extending, we have to consider local co-cycles, and this will allow the always grading to the central extension. Well, local means that, again, something like, ideally, this is, if we take the Virasoro co-cycle, so we have only a contribution if n plus m is 0. Okay, but here now we have to, so we have to we relax this again. It is if it has to be 0 outside a certain band around this here. And now this is called this would be the local. But now the point is bounded one plays a role also in this. Well, even what I do today, but okay. So it means that it's bounded here that. At least if it is n plus m is big, then it should vanish. Okay, good. For the classes, it means that it contains one representing cocycle of this type. So. Okay, good. What I did, I classified all local and bounded cocycle classes for all this geometric situation here. But, okay. Now I have to see how I have to make a certain shortcut that I at least maybe can end with this here. Now the point is, let me do this. Skip to the, maybe. Okay, good. Maybe. Okay, the main philosophy, the genus theory, is that we show that all cocycle classes are geometric cocycle class. In this genus 0 case, okay, up to the number of points, that all cocycles are bounded with respect to the standard splitting. And now we use this classification results and so on. My classification results are about this. And now we can really write them down and so on and so on. And we even give then the universal central extension. Can be, no, sorry, this was again the wrong. Again, the wrong pointer. We can, so the universal central can be given directly by integrating, okay, by integrating the stuff there. But the details, this is not enough time left anymore. And so this would be, if you like, you can just download the presentation and have a closer look on this. Let me skip to this situation. So good. The shortcut is like this. These are the cocycles which play a role there. So this is for the function. This is for the vector fields, where R is a projective connection, which will be 0 for with respect to the standard covering of the Riemann sphere. This would be for differential operators, and this would be the affine stuff here. And sorry, and let me go back. The point is, you see, we obtain, you see, what we obtain by this process. We have, these are the universal differential forms which we integrate, okay? And we integrate it over all curves. And by this, we get indeed all cocycles. We get all Lie-algebra cocycles by integrating over all cycle classes. Over all cycle classes. This means that H lower 1 of sigma minus A set gives exactly all the elements of the Lie-algebra 2 cocycle in this situation here. So this gives you the dimension, because you see, this is the unique stuff here. Only here plays the role. Here, again, only 1. Here, you see, differential operators, you get this one, and this one, okay? So this will be then 3, okay, good. And now this one, which is integrated over the separating cocycle, this gives the unique local one always in. But I said I will make a few comments if you allow. So a few comments to the 3-point algebra. The point, because in the 3-point algebra, meaning, so we have now 3 points. This I put to infinity, now we have 0, 1. You see, that is 3-point algebra. We can normalize the stuff by a conformal transformation that the 3 points are mapped to 0, 1, and infinity. Good. So, and now, still now the question about choosing the separating cycle, okay? Here, this means what are the out points and so on. I could take, for example, this one, okay? Then this one, the I, and these are the O points. The point is that there are others. For example, I could take this one, okay? Still 2 points in one. Yeah, okay. In this case, you see, I could write 0, 1, infinity, or I could have to consider another one, which is 0, infinity, O is equal to 1. These are not equivalent, these are different splittings, okay? Good. But it should be equivalent by the exactly. This is a very special situation that in this case, there is, we have the algebra corresponding to this situation. And then we have different splitting. But now we have something because by the conformal transformation, we have a certain automorphism of the algebra, which transforms one decomposition, one splitting into the other one, okay? So, what? No. This is one choice. So if we have this. We have to fix. We have to put 0, 1, infinity to 1 point to some. We have this 3 point put 0, 1, infinity, and now we have to take a splitting. Okay, good. And now I take in the presentation 0 and 1, 0 and 1. And the outcome will be the infinity. But who, for example, you want to say, okay, why you don't take the infinity and the 1, or the 0 in this case, to be the incoming points and the other one the outgoing points? this is a choice. It is a reasonable choice. For the genus 0 3-point situation, we have 3 different splittings. These 3 different splittings meaning that we have 3. Okay, good. So, so good. Maybe then we should discuss this then later, because. But as you remarked, this conformal transformation allows one to it's an automorphism of the algebra which shifts the splitting there. Well, it's a very special situation. If I have 4 points, this does not work anymore. Okay, but let me say, okay, we have this there, and then we have this the structure equations, so we can write it down. And so let me at least show you this. At this page where I do the calculation of the cocycles, you see 3 points means we have the homology is 2-dimensional. So we have 2 different cocycle class, really different one. The first one would be the gamma 1, and the other one would be the gamma 0. This integration around 0 means separating. This one is not separating. And now you see exactly what I meant about this. This cocycle there, this is local. I can use for the representations. This one is not local. So, because this one will never stop. So n and m, if n and m are big, it will not stop. So this one is not good for representations. So this one is non-local, it's not good for representations. Okay, I see there are a lot of different, of course, a lot of things because I was very fast at the end. Okay, good. Maybe if I know some more, then you have it here, or you just ask me when I'm around. Okay, good, thank you very much.